Thanks. Begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Thank you for letting the rain stop. And thank you for not letting us get washed away. I just pray you be with this class. Help us to glorify you, Lord, in what we do this day. And again, Lord, I thank you for your many blessings to us. In your name I pray, Lord Jesus. Amen. All right. So what I want to talk to you about today is it's somewhat different than other lectures I've given you lately. So here I'm going to show you, basically I'm going to try to describe to you today, as best as I can in the time we have, how you can do calculations in coordinate systems other than the XYZ coordinate system. So if I had to give a title, I'd say I want to talk about vector calculus in non-Cartesian coordinates. Now that's a little bit too ambitious, because really all I'm going to talk to you about is how to either do it in polar coordinates, which then leads naturally to cylindricals, or I'm going to tell you about how to do it in spherical coordinates. All right. So the first chapter in this book has to do with just the algebra. How can you express a vector field in terms of, they say, the polar, or, well, let's start with the polar case. Right? So the basic thing is we take a point, right? And we can label that point by the standard angle and the distance. So we have x is equal to r cosine theta, and we have y is equal to r sine theta, right? And we derived the other day that you can talk about r hat and theta hat, right? Was what? It was cosine theta, sine theta, or you might write it cosine theta x hat plus sine theta y hat. And you can talk about theta hat. Theta hat was minus sine theta x hat plus cosine theta y hat. So these are your basic building blocks. To write a vector field in terms of the polar coordinate frame, you want to use r hat and theta hat. You want to use r and theta. So as a typical example, if I have a vector field, say f of xy equal to, x squared plus y squared, and then I'll make this really easy on myself, tangent of y over x, how would you convert that? How would you convert that to a corresponding, how would you write that in polar coordinates is really my question. So by default here, what we mean, of course, is x squared plus y squared x hat, right? Plus tangent of y over x. Oh, I'm sorry. I say tangent. I meant tangent inverse. I'm not being lazy enough yet. Y hat. Everybody with me so far? So here's a vector field. I've written it in terms of Cartesian coordinates. How do you rewrite that in terms of polar coordinates? Great. So you're like, well, that's obviously r squared x hat, right? And this is theta y hat. But we haven't sold out completely to polar coordinates just yet, right? Because you've still got x hat and y hat there. We'd want to convert those to what? We want to somehow convert x hat and y hat to r hat and theta hat, right? So what is, what is, how can you find what x hat and y hat are in terms of r hat and theta hat? Well, there are various methods. Let me show you one. So I can take this right here, right? And if you look at this, I can write x hat. X hat's going to be what? It's going to be x hat dot r hat, r hat plus x hat dot theta hat, right? So what is that? Can you figure out what x dot r hat is and x dot theta hat is from these expressions I'm circling? I know this is possible because I know that r hat and theta hat are linearly independent. They're different directions, so I can build any vector in 2 dimensions by using those two. And they're orthogonal, so I can use dot products to select the components, right? I'm using the projection idea here. What is this? Well, look at this, right? Take the dot product of this with r hat. What do you get? R hat, yeah, 1 equals cosine theta. And then what else? How about theta hat? X dot theta hat. Well, this one, right? Theta hat dot this expression is minus sine theta, right? So what's y hat equal to? Should be y hat dot r hat, right? And you guys are about to tell me the answer. You guys like to tell me answers. So you say it's sine theta, r hat, yeah. And then what? Yeah, plus cosine theta, theta hat. Which is not too shabby, right? The alternative to this would be you got 2 equations and 2 unknowns, right? You can solve this for x hat and y hat just using substitution in algebra. But I think dot products beat the pants off algebra when you can do them, right? Once I had the idea, it took me relatively little mental energy to derive those. Now that I have those, right, I can put those up in here. What do we get? X hat apparently was cosine theta r hat minus sine theta theta hat plus theta times y hat, which is sine theta r hat plus cosine theta theta hat. So just to collect things together, I've got myself an r squared cosine theta plus theta sine theta r hat plus parentheses, let's see here, what's the theta term? Minus r squared sine theta. What else do I have? Plus a theta cosine theta theta hat, right? I think now at this point we have earned the respect of those who live in the kingdom of polar coordinates, right? This is legit. You can't be more polar than this, right? I mean, it's all polar coordinates. It's polar coordinate frame, the r hat, the theta hat, and functions of r and theta, right? That's it. In this notation, this is what's called f sub r. Oh, I'm sorry, big F sub r. And this is what's called big F sub theta. It's the r component and the theta component, right? And if you want a formula for that, well, f dot r hat is equal to this, right? And f dot theta hat is equal to that. So it's the r component and the theta component. Just like in the original thing, right? Just to bring it back to the Cartesian world again, up here you could write fx x hat plus fy y hat, where what? Fx was equal to like f dot x hat, and fy is equal to f dot y hat, right? So there's nothing terribly, the things I'm telling you about dot products, they're not new. It's also with us at the level of the Cartesian coordinates. We just don't always think about it that much because they're just kind of there, and we don't. But the r hat and theta hat are interesting, right? Because they change from point to point. You guys with me? So, natural question to ask once this world is open to you is how to calculate the gradient, right? Actually, I'm taking a step back here a little bit. In other words, suppose I have f as a function of r and theta equals blah. All right? But the blah is just in terms of r and theta, right? what does the gradient of f look like in terms of r hat and theta hat? How would you figure that out? It should be partial derivatives of blah, for sure, right? For sure. And it should definitely also be the case that this is equal to, the gradient that we already know and love, right? If we convert this over into Cartesian coordinates, it should still be this thing, right? With the appropriate identifications, it should be partial f partial x x hat plus partial f partial y y hat. Right? Because geometrically, the gradient is this thing that you can calculate, and the Cartesian coordinates just gives you one description of it. But the polar coordinates just give you a different description of it. We don't know yet what that is, but we're going to try to find it right now.
Wait, so you're saying maybe you're going to come back and write things in those two blank spots you left?
Yeah, right. The question is what goes here. We would like to fill in the blanks, yes. Now, our definition of the gradient, right, because we don't know any better, is this. This is the definition of the gradient. But, technically speaking, there's an abuse of language here, right? Because you can't have a function of r and theta and also a function of x and y. There's got to be some coordinate change between the two, right? Like, perhaps I should call this thing g of r theta. How would g and f relate? Again, they're the same function, they're just written in different coordinates. G of r theta should be f of what? How do you make x and y out of r and theta? Right. So for example, if I had g of r theta equals to r squared plus the tangent of theta, then that tells me what's my f of xy then? I heard it. I didn't hear the last thing though. Divide. Of course, assuming that we're where x is not 0. X being 0 makes tangent hard to understand. But supposing we're not at one of those malevolent points, this is y over x. Anyway, if I'm talking about this function, I'm talking about a place where tangent's defined. So certainly I'm not allowed to be where x is equal to 0. AKA plus or minus pi over 2. Standard angle. So there it is. But you see that if you actually plug into this expression r cosine theta and r sine theta, you get back to here, right? See the correspondence? We did it intuitively over here. But formally, this is the equation that connects these two things. But it is nevertheless often the case that when you read engineering books or math books at this level, they will use the same function, whether it's a function of x and y or a function of r and theta. Like some people would use both f and g for both of these things. But when you're trying to understand the connection between the two, if you don't make a distinction, it's hard to see what you're doing. All right. So what I'm trying to get at here is that the question mark should involve the g, not the f. What's that?
Do they at least put in a little notation for like which one's in polar and which one's in Cartesian? With the thing you're talking about where they use same letter for their equation?
Yeah, I mean, like, people will talk about partial f, partial x, and they'll talk about partial f, partial r in the same breath, whereas this is actually a function of x and y, whereas they're not really differentiating f, they're differentiating f composed with the r cosine theta for x and the r sine theta for y, right? So when you see partial f, partial r, what that's actually saying is partial r of f of r cosine theta, r sine theta. It means what it has to mean. But at the same point, it's kind of an abusive language in some sense because they're not the same function, right? As much as they are philosophically the same function. Okay, enough philosophy. I don't want to be accused of teaching you philosophy. Let's get back to something useful. Oh, I'm sorry. Philosophy is useful for philosophers. I digress. All right. What should we do? We would like to discover the formula for the question mark. Any ideas? Oh, try to derive it from the current example? Well, that's hardcore. Oh, well, first of all, that's no help to us also, because this was a vector field, and I changed gears. Now I'm saying take a gradient of a function. I'm just showcasing for you the r hat, theta hat stuff over here. I'm asking a somewhat disconnected question. Tell you what, let me call this thing, let's do some name calling. Let's say that this is A r hat plus B theta hat, and we'd like to find out what A and B are. And let's do some more, let's say a little bit more than that. We also expect that we're going to need to relate, we're going to need to think about this issue. So for example, partial r of f of r cosine theta, r sine theta, what's that equal to? Partial, exactly. True. That would be partial g, partial r, right? But also the chain rule, right? So this is the x spot. This is the y spot. So the chain rule tells me that this is partial f. So I guess to be more, it's technically I guess it's partial g, partial x, right? Oh, fine. Now you guys got me all in a tither. Partial f, partial, I guess it's my fault. Partial f, partial x, partial r, right? Plus partial f, partial y, partial r. But in some sense, that kind of seems, I mean, we know what these are. What's partial x, partial r? I'll do the cosine. It's a cosine theta, partial f, partial x, right? And what's the other term? What's partial y, partial r? What would the partial derivative with respect to theta be? We'd have. Oh, you're telling me the answer. Fair enough. Sorry, let me write in between steps. So the chain rule, and then partial x, partial theta was what? Minus r sine theta. Partial f, partial x, plus r cosine theta, right? So there's some kind of relation between the derivatives of the g and the derivatives of the f. This isn't very helpful to us, though, is it? I mean, it's not quite what I want, because the sort of natural jumping off point for me here would be to plug in these partial derivatives, rewritten, right? I mean, let's see, what's a game plan? Here's a game plan. There's different ways you can do this calculation. I'm just showing you one. I can convert partial f, partial x to r's and thetas. I can convert partial f, partial y to r's and theta, right? We already figured out over there how to rewrite x hat and y hat in terms of r hat and theta hat, right? So if you put all that together, that should give us the expression we want. So the annoying thing about my work so far is that it's useless for our purpose, right? Because we want partial f, partial x. What do I have up here? Right. So what should I do? Well, there's a couple different ways I could go. But what I'm going to do is I'm going to go ahead and work on it right here. And I'm going to just take a leap of faith here and see what happens if I put in what we found for x hat and for y hat into the definition. All right? So partial f, partial x, x hat, that's my partial f, partial x times x hat, which was what? Cosine theta r hat minus sine theta theta hat, right? Plus partial f, partial y. And then what was y hat? Sine theta r hat, what? Plus cosine theta theta hat, great. And then why don't I just regroup terms so that I have an r hat and a theta hat? So I got myself like a cosine theta, partial f, partial x, plus sine theta, partial f, partial y. This is starting to look encouraging because it's starting to look like things we calculated above, right? Check that out. To quote your generation, sweet. Oh, I'm sorry, was that so 5 years ago? No, it's still, the sweetness is still there? All right. What's next? Parentheses. What you guys got against parentheses? I tell you, parentheses, it's a sad day for parentheses these days. Parentheses they're underappreciated in the tests and homeworks of so many of my students. It's here. Actually, I'm not so much talking about you guys. I'm talking about the 126 crowd. It's like it hurts their hand to write a parenthesis sometimes. And then, like, what's up with the people who do this? Like, is it so much? Is it so much to do this? Like, ah! Sorry. I'm not sure whether that has anything. It has absolutely nothing to do with what we're doing. Sorry about that. I think my mind just skipped. I saw some thing last night on vinyl records. I guess that was what did that. So that is partial G, partial R, right? And that's not quite partial G, partial theta, is it? You see what you got up there? See that R? There's no R here. How can I make an R from nothing? Yeah, divide it. But then I also have to multiply it, right? Well, that's what you're telling me, basically, right? So we multiplied by 1. In so doing, we divided by R, and we created a partial G, partial theta. So what's A and B? Now we can tell you what is A. Partial G, partial R. And what is B? Right. And now we know how to calculate the gradient of a function in polar coordinates. Which means we can also do cylindrical coordinates, right? How about this? What if I have f of r theta z equals to r squared plus theta cubed plus z to the 14th power. The gradient of f will be what? I'm sorry, I made this too weird, didn't I? Here, let me make it less weird. How about r cosine theta plus z squared there. So the formula is partial f partial r r hat plus 1 over r partial f partial theta theta hat plus, guess what happens with z? Nothing. Z plays the same role in cylindrical coordinates as it does in Cartesian coordinates, so you already know the story over here. It's partial f partial z, z hat. Generically speaking, here's an intuition. If you have a coordinate system and one of the coordinates is a linear coordinate, then in the gradient it will just be partial derivative with respect to that coordinate times the hat of the coordinate. So like partial f partial x x hat's an example of this, partial f partial r r hat. When we study spherical coordinates, there'll be a term in the gradient which is partial f partial rho rho hat. But the angular, the curved coordinates, those will be weird. Der. Okay, so what happens? Yeah? Oh, nothing? Looks like I've got 2r plus cosine theta, r hat, right? Plus 1 over r. What's partial f partial theta? Minus r sine theta, right? Theta hat plus 2z z hat. And there you have it. That's the gradient. Now, admittedly, this one it'd be kind of interesting to compare this to the, well, this one's actually not a good one. I mean, I can compare this to the Cartesian coordinates, but it wouldn't be too exciting. What would the corresponding Cartesian function be? I'll use h this time. What's h of x, y, z that's kind of corresponding to this? It would be what? X squared plus y squared plus what?
X.
Plus x plus z squared. So that gives me a gradient of h. I've got 2x plus 1 x hat, right? Plus 2y y hat plus 2z z hat. So, I mean, this example is probably easier in Cartesians. Here's what I typically do if I test on this. My typical move is something like this, you guys. Here's a typical question. It's kind of rude, but it serves its purpose. Let f of x, y equal to the 1 over the square root of x squared plus y squared times the inverse tangent of y over x plus the, gee, I don't know, sorry, I'm thinking. Oh, that's enough. That suffices. Calculate the gradient. Actually, that's sufficiently horrible. Calculate the gradient. And then I'll have some little thing like use any coordinates that you'd like. Now, for those of you who are so foolish as to attack this problem in Cartesian coordinates, woe to you. Because as you can see, the differentiation in Cartesian coordinates is quite awful. Right? But in polar coordinates, this stupid thing is just what? I mean, this is, if you'll forgive this abuse of notation. Fine, no air quotes. It's 1 over, yeah, it's 1 over r theta. Right, so the gradient of f is just partial r of 1 over r theta, theta hat, plus 1 over r, partial theta of 1 over r theta, theta hat by what we derived today. Oh, yeah, thanks. I do that. And so minus 1 over r squared theta, r hat, plus 1 over r minus 1 over r theta squared, theta hat. And I guess I could, fine, I'll clean it up. You asked me to, so I will. So this is 1 over r squared theta. I'll put a minus out here. Minus 1 over r squared theta, and that's r hat. Plus 1 over theta hat, I suppose. If we had done this in Cartesian coordinates, we'd still be differentiating. And we probably would have gotten it wrong. And while this is still a complicated example, you at least have some hope of analyzing it with this formula, right? There's also a geometric side to what we're doing. It's very, very freeing to be able to write vector fields in terms of the other coordinate frames. Let me show you. Let me apply what we're doing to something for just a second. So, for example, let me take us back. We had f of xy equals to x squared plus y squared. That was one of the first things I analyzed the gradient of in terms of the level curves and such. Right? It wasn't too bad, but now it's stupidly easy. See, the gradient of f is partial r of r squared, r hat. I don't really need to write this other term, right? So you can see from this, what do I have? I've got 2r hat. So what is this geometrically? The gradient just points outward in the polar direction, and it increases faster and faster the further you go away from the origin. We actually had to work a little bit to understand that when we use Cartesian coordinates. I had to draw a few arrows, try to convince you that x comma y was I was pointing out. If you understand geometrically what r hat is, it's immediately obvious what this is doing. And there's other examples. For example, if maybe you'll study in electromagnetism, something like a current which flows out of the board. So if the current flows at you, like that, out of the board, the magnetic field wraps cylindrically around the wire. You take your right hand, you point your thumb in the direction of the current. The way your fingers wrap around the wire is the direction of the magnetic field in circles. So the so-called field lines are something like this. This is an integral curve to the magnetic field. They're like this. Those are supposed to be circles. What I mean, though, is if you take a particular point, the magnetic field looks like this. Now, I've done, this is not right. My picture should be the opposite way around. The arrows should be getting shorter out here in terms of magnitude, right? Because the further you're away from the wire, the weaker the magnetic field goes. Now, you'll derive from Ampere's law that the magnitude of the magnetic field is mu naught over 2 pi r, where r is the distance to the field point from the source point. In this case, the source current. With the polar coordinate frame, I can do better than just write the magnitude of the magnetic field. I can write a description of it in terms of the polar coordinate frame, well, cylindrical, 3 dimensions, right? Which is just this. What's the formula? That's the magnitude. What's the direction? If the z-axis is pointing out at you, what is this vector field that wraps? Yeah.
Theta hat.
That's theta hat, exactly. If I tried to express that in Cartesian coordinates, it'd be a mess.
And nobody can read it.
Right, but when you look at that, if you know what theta hat is, you know immediately what this field is. Another example of this in the spherical coordinates if you have a point charge at the origin, Q, right, the Coulomb law says that the electric field is equal to KQ over rho squared. In calculus 3 notation, that's the magnitude. K is a constant. If you like, maybe you saw it this way before. 1 over 4 pi epsilon naught, where epsilon naught is the permittivity of free space. Q is the charge in coulombs, and rho squared, well, that's the distance. That's the distance from the source charge Q to a point out here. And which direction does the electric field point then? Radially away, right? And it's the same no matter where you are. It always points directly away from the origin. Right, so if I was to be so foolish as to plot more of them, they're like this, you know? So what, if I want to write a vector equation, what is this? E is equal to what? I'll do the easy part. Q over 4 pi epsilon naught. Well, I don't know why I stopped writing K. K is easier. Rho squared. Rho hat, right. That's exactly it. Because it points spherically outward in the direction of increasing spherical radius from the origin. So, in tune with the question that I asked you on the homework, we can ask a question which is, this is equal to minus the gradient of what function? Oh, phi is a bad choice. Let's say u. Still a bad choice. Let's say v. Because that's what this is, it's the voltage. If you take the gradient of the voltage function and put a minus out front, that should give the electric field. This is what we learn in Physics 232. All right, I'm not going to try to teach you physics in here, but we'll try to teach you some calculus. How do you find v then? What would we need in order to construct the v? So let me state the problem. Let's get rid of the constants, right? So we want 1 over rho squared, rho hat, to equal to the gradient of some function. And tell you what, I'll just call it f. So here I set v equals to f as to, I don't know, just because I did. To make more of a connection with the stuff we were doing earlier, I suppose. So what would I need? I would need to know the formula for the gradient in terms of spherical coordinates, right? And so this would be equal to what? From what we've already done today, if you believe my intuition, it should be partial f partial rho hat plus some complicated stuff, theta hat, plus some other complicated stuff, phi hat, right? Where remember we derived the theta hat and the phi hat? Well, theta hat we have over here. It's this. Still that theta hat. But the phi hat was somewhat complicated. I don't remember it right off the top of my head. And, okay, I mean, honestly, folks, it would take me about 20 minutes, maybe a half hour, depending how fast I work, to derive what's in these parentheses. Okay? But the thing is, we don't really need that to answer this question, right? Sufficient to say you don't want to have some kind of theta or phi dependence, because that might generate something over here in the theta hat or phi hat direction, right? But the thing we're trying to produce over here has no angular dependence, right? It's just in terms of the spherical radius. It's got this so-called spherical symmetry. So what would f be? Yeah? Yeah, f is basically just the integral of 1 over rho squared, right? D rho. Oh, minus v. Sorry. And so this is what? Minus 1 over rho, right? Plus some constant. But we'll just set the constant to 0 because we can. And so there you have it. The potential then, putting the constants back in that you'd want would be something like q over 4 pi epsilon naught rho. And indeed, that is the so-called Coulomb potential. If you take the gradient of that, you get back the Coulomb field. You get the 1 over rho squared rho hat field. There's a question you should ask me here. What is it? I guess there's a few questions. The one is what's in the question marks, right? Let me just tell you what goes there without deriving it, if you don't mind. This is Cully's Vector Calculus, which is a nice book. Well, the more recent editions are kind of expensive, so I guess I wouldn't use it even if I had the freedom. But the first edition you can get for about $5. It's kind of nice. This is a first edition. Anyway, and here she actually has most of the derivation of this, what we've been doing today, and more. But here's the formula for the spherical case. I don't have it memorized, by the way. Partial f, partial, but then again, I wouldn't need to memorize it if I was in this class because I'd have a note card, right? I just need to know how to use it. Hopefully her spherical coordinates are like ours. 1 over rho, partial f, partial phi hat, plus 1 over rho. Now this makes a lot of sense actually if you think about it. 1 over rho sine phi, partial f, partial theta, theta hat. Can you guys tell me why this last term makes a lot of sense? I think it does. What's the relation between cylindrical and spherical coordinates? So if this is the angle phi, right? This is the angle phi. The spherical radius is rho, right? What's this down here? It's r. What's it also equal to, though? So you see, this is just r. It's exactly the term we derived. Where did I put it? Did I erase it? I might have erased it. The thing we derived. It's the 1 over r partial f partial theta, right? Just written in spherical coordinates. We don't have r to work with in sphericals, right? So instead of writing r, we write rho sine theta. But that's actually rather unsurprising from that viewpoint. So this is what was missing in the question marks over here, and you can see that my derivation was legit, right? I mean, we definitely don't want a theta or a phi dependence, right? Now, what if we were to attack this problem in terms of Cartesian coordinates? What would it have looked like? A mess? Yeah, our E would have been something like Q over 4 pi epsilon times x squared plus y squared plus z squared, right? Rho hat. So I can take this to the 3/2 power and write this as x, y, z. So what I did here, guys, is to point out that if you can do 1 over rho squared rho hat, you can rewrite that as 1 over rho cubed times rho hat. And rho hat is just x, y, z. So that, we would have had to figure out this thing equals to the gradient of, find f that solves that. I mean, you could set the q over 4 pi epsilon naught equal to 1 if you want, but still, you see how much worse it is. It's so much easier to solve a problem that has spherical symmetry by using the right tool, which is spherical coordinates. And many of you are engineers, so this should matter to you because you're interested in solving problems that involve spheres and cylinders and things like that. Like, I don't know, what's this?
Extruded cylinder.
Yes, it's exactly what it is. It's extruded cylinder. So this has that cylindrical geometry if you zoom in locally. So you want to be able to analyze that because coax matters, among other things. Spheres are at the base of electrostatics and also gravity. Some of us want to understand gravity, right? I mean, it's kind of hard to avoid. You guys ever seen Fringe? There's this great time in Fringe where people start losing gravity, and then so if they're not careful, if they don't wear the right shoes, they'll just fly up into the sky. It's great, right? But that makes an interesting story, right? Because it doesn't happen. So of course, the force of gravity is similarly described by these things. But later, much later in the course, I have more to say about this. We will eventually study something called the divergence of a vector field. Divergence. And we'll study something else called the curl. These will reveal the geometry of vector fields themselves. We study that the last maybe 20-30% of the course, all right? And so when we get back to that, again, we'll have to ask this question. How would you write the divergence and curl in terms of the other coordinate systems? But anyway, that's 6 weeks off or something like that at the moment, I think. So tomorrow, what should we do? What's on the course planner? What's that? Somebody have a course planner? Andy? It's a race. Who will win? Who will win? Who will win? Oh, yeah. Aha! Thank you. Fall break. Do we have a fall break? Right. So we are now to exact differential equations. So I think tomorrow I owe you. Oh, I'm sorry, I skipped ahead. I just covered gradients and curvilinear coordinates. That was supposed to happen. We just experienced some time travel. That was supposed to happen on October 6th. What have I done?
Oh, now we can't have class on October 6th.
Oh man, I was going to do a Tuesday, Thursday class on this. I just fit it into a Monday, Wednesday, Friday class. You guys should be upset. No, tomorrow we'll cover exact differential equations, and then I think we can take Friday off again. But the mission is due on Wednesday. See, I would like to make class no class on Wednesday, but the trouble is when I do that, then all of a sudden people are like, well, I just forgot to turn in my mission. So if you guys can universally promise me that we are not going to have that conversation as a consequence of me canceling class next Wednesday, we could do it.
Well, you can make that person come in and turn in on Wednesday.
I mean, you can turn in the mission earlier on Wednesday, right? Or later on Tuesday. Yeah, in office hours. Yeah, okay, so I will plan to not have class Wednesday before fall break. And, because of that, we'll meet Friday, yeah. So, but I think after tomorrow we should be done with the new material, so we should have about 2 days to just talk about your life, or whatever it is you want to talk about. Maybe math. Math would be good.
So when is the mission due now?
Mission's still due Wednesday, but there won't be class. You can just turn it in.
So just
Bring it to my office, yeah. Thank you. See you guys.